Okay, hello everyone, and welcome to the lecture. So, can you please confirm if you can hear me and see my screen?
I can hear you and see your screen.
Thank you.
Yeah, all good.
Thank you. Okay, so before we start today's lecture, I just need to talk about a couple of things. First, I have actually I also made announcements, but I want to mention it here too that I have graded the reading notes 1. I have not yet graded reading note 2 and 3. Uh, And what I want to mention is like, yeah, I have provided comments there, so please go through those comments for like each of you. I have given comments in the while I was grading the submission. Uh, my one observation is like your summaries, they are too well written, right? Like too well written in the like to the level where like well established and well established researchers are writing, right? So I am like kind of surprised, but my feeling is I hope I'm wrong. My feeling is like students are using AI tools. Please, if you're doing that, please don't do that. Stop using it. I mean, it's fine to write a summary which maybe is not perfect, but it should reflect your understanding, right? Uh, Remember that it is an opportunity for you to learn, right? Learn how to summarize reading of sections or reading of a full research paper, right? So use this opportunity for your benefit. And again, uh, I have not deducted any points when I was grading the reading point 1 for summaries, which were like looking like they are like AI generated. But I will not be that much lenient in future submissions. And if I feel like this is not summary written by an undergrad student, and again, I can be wrong. Maybe you are much better than me in writing summaries, maybe because you are native speaker, so you know how to write a good summary, and maybe I'm not that much fine. So, but if I feel like this is not, which is at the, at the level of an undergrad student, I may ask you to meet me in office hours to discuss your summary, okay? And your understanding of the of whatever we have read. One thing, second, I also noted that the annotation of the file which was required, all of you have provided, but most of them are poorly annotated. What I mean by poorly annotated is like some students, they have like just highlighted a couple of paragraphs, a couple of sentences, or maybe three, four sentences, right? That is not the purpose of annotation. Purpose of annotation is actually to uh, uh, emphasize or like bring to the forefront the main concepts of the section which you have read. So please highlight all the important things which are like, for example, new for you, or if you have a question while you are reading, write that question in the annotated file. Similarly, if you have comment or some confusion, write it there. Question, so write the answer to there and point them like, okay, this is the question and this is the answer. I found it here and it is mentioned here. Okay. So like again, use it as a learning opportunity, right? So I have not deducted points, but in future submission I will deduct points if your annotated files are not in a good form. Okay. Now uh, uh, we will actually follow the same pattern which we have used in the previous lecture. One thing, I was worried, and I am actually still worried that I am kind of slow as compared to the tentative schedule. But again, I don't want to sacrifice your understanding of the material because this is like background, a very basic stuff, which will be actually helpful for you while you will be reading the other papers. So yeah, you will be like submitting the reading notes for the sections which we have not yet covered. So there is a kind of mismatch what we are covering in the lecture and what you are reading and submitting in the reading notes. But that's fine. Okay. So I will try to my best to cover as much of this paper as possible, but then we need to put a limit, which is week 6, and then at week 6 we stop. Okay. Okay. And another thing, sorry, your presentations are coming up. Your first presentation is on 18th of February. So if you, it is not required, but I will strongly encourage you to send me your presentation slides uh, at least a week before your presentation day so that I can give you the feedback and then you can improve your slides based on the feedback. So if you get the feedback and you improve it, it's mean you have chances of getting higher score as compared to a student who doesn't seek the feedback and directly go and present the slides. Okay. Okay. So, okay, remember last time what we were talking about? We were talking about address translation, right? Why there is a need for having a virtual memory and a physical memory, and then how virtual addresses or virtual page numbers are translated into physical addresses or physical page number or frame numbers, right? So then we talked about also in that discussion about the page tables. So remember they were like it was hierarchical page table. First you have this what was this level? Let me do I have actually yeah I guess I have it in this slide too. So let me quickly refer here. Yeah, so at the top you have PML4, and then you have PDP, PML4, page map level 4, then you have page directory pointer table, then you have page directory, then you have page table, right? Now, page table is the last level, right? So page table, as clear from the name, it has entries. So what is the content of each entry in a page table? So each table at page and each page table entry, I need to slow down. Okay. Yeah. First, if you have any questions about what are the contents of an entry in the page table, please write those questions in the chat. Any questions about content of the page table entry, please write them in the chat. And if you don't have a question, please write no question. Okay. Okay, so each page table entry, it contains a physical address and some flags. So if you remember from, actually instead of drawing, it's faster if I can show you the content from the previous. So here, you can see that these are 4 levels like 1, 2, 3, and 4. So at the 4th level, you have like if you like the lowest level, you have the page table, right? So actually whole of it is called the page table and it is called hierarchical page table. But for historical reason, because initially the page table was not hierarchical, it was a single level, right? So that's why we still name the last level as the page table and we give different name to other pages, other levels. But actually the whole thing is known as the page table. So now what is the content of the entry in this page table like? So you have this one entry here, right? So what is the content? So in the content you have physical page number. Remember, we said that you divide. So physical page number is actually the frame number here, frame number of the physical memory, right? Just like here, 1, 2, right? So you have the frame number. Sorry. Why? I don't want to go through this all animation. It's a long animation. Okay. So we in each entry we have the physical page number which is same as the frame number, a different number for the same thing, but that is not the only thing. So if you have a table here, this is page table, you have entry here. In this entry you have frame number, or you can name it as physical page number, right? And other than that, there is also some other information here, right, in the same entry. What is that information? So that information, actually we have a set of flags here, right? So what are those flags? We are going to talk about them, okay? So what information they convey? So first flag is present flag, it actually tells us that whether this physical page is associated with the virtual address or not. So if the physical page is not associated with any virtual address, so the value of the flag is equal to 0, right? So, but if the virtual address is associated with the physical page, the value of the flag is equal to 1. And when I'm covering the slide, if some questions, you have some questions, then just take a note and at the end I will take care of them. Okay, access flag, it is actually set to 1 by the CPU whenever the address translation reads a table entry. Okay, whenever it reads a page table entry, so it sets the flag of that page table entry, a flag equal to 1, which means that this page is accessed, right? Dirty flag, dirty flag basically mean the flag, it tells us that the given page, whether it has been modified or not, right? So how it is modified? By doing write operation on the page. So if the CPU writes data on the page, then it sets the dirty flag or D flag equal to 1, which means that the page is modified. Remember, from where we bring the pages in? From disk. So if you write, it means that there is a mismatch between the version of the page in the disk and version of the page in the physical memory. So the page in the physical memory is now dirty. Writable flag. So actually, there are different kind of pages. In the code, the application is divided into pages, remember, and depending upon whether a page contains the code or it contains the data, it can be it can be written or it can be not written. For example, the code cannot be modified, right? So that's why the code pages, they are not writable. However, the data pages, when you update the data in memory, so it's mean you are actually writing the page of that application, data page of that application. So this flag is set equal to 0 to prohibits writes to the memory locations inside a page. Not only for code pages you set a write flag equal to 0, but even if there is a data page which you don't want to update because of some reason, then operating system can set its write flag equal to 0. So if its write flag is equal to 0, it's mean it is not allowed to modify that page. It is not allowed to write that page. Disable execution. Remember, I said that pages can be like code pages or data pages. So we can execute the code only whatever we read from the pages, we can execute it only if it is read from the code page. If you read the content from the data page, it should not be executable, right? Because data is not an instruction. However, hardware doesn't understand. For hardware, instructions is just a stream of bits, right? Machine code, if you remember from your machine organization course, right? So we need to inform the hardware that this page contains code, and that's why it can be executed, and the data pages, they contain the data and they cannot be executed, right? So if a page is not allowed to be executed, so the disable execution flag, it will be set equal to 1 by the operating system. Supervisor flag, this flag is set to 1 to prohibit access from application software running at ring 3, which basically mean that this page, for if a page has a supervisor flag set equal to 1, it's mean maybe it contains the kernel level code or kernel level data, or some higher privilege software, for example hypervisor code or SMMM code. Okay, so okay, let me check if there are any questions. No question. Where can we find the Excel sheet where we signed up for the presentations? Okay, please remind me this question at the end of the lecture. Okay, I think someone answered. Thank you. Okay. Uh, okay. So here is a question for you. Who set all these flags? Like present flag, access flag, dirty flag, writable flag, disable execution, and supervisor flag. Who set these flags on the pages? Who's responsible for controlling these flags? Uh, yeah, can you give me a reason why? I think it's faster if you unmute yourself and talk. Dental management engine.
Um, I don't really have a concrete reason. That's just a guess.
Okay. Uh, yeah, your guess is correct. The operating system is basically responsible for that. Why? Because remember, where are these pages located? All of these pages are inside the page table. And who is managing the page table? Operating system manages the page tables for the user level processes, and hypervisor, it manages the extended page table, which we'll talk about in a minute. Extended page table of all the virtual or guest operating systems, right? So that's why only system software can modify these or update these flags. Okay, so let's continue. Uh, so address translation and virtualization. So in previous slides, we have basically talked about only about the non-virtualized environment, which means that we don't have, and we are running only single operating system on a machine, right? Now, in the virtualized environment, what we have is like we have two layers of indirections. So previously, what we had an operating system, right? And it was running the processes, and the addresses generated by processes, they were sorry, it was not running, it was managing the processes, and the addresses generated by processes, they were virtual addresses, right? So what was our job? To convert them from the virtual address to the physical address, right? So but in the virtualization environment, what we have the physical address or physical memory, right? And that physical memory is multiplexed among multiple guest physical addresses, among multiple guest operating systems, right? And then each of the guest operating system is running multiple user processes, right? So what happens is that a virtual address generated by a process, it is first mapped using the page tables into the guest physical address. This time we are not saying physical address. It is mapped into guest physical address. But this guest physical address is not real physical address. So it is like just like process has an understanding, or process sees the virtual addresses, in the same way the guest operating system sees the guest physical addresses, which are not real physical addresses. But then we need to convert them or map them into the physical addresses using extended page tables. So actually we are doing two level of address translation. First, from earlier, what we were converting from virtual to physical address, because we had only one operating system and it was running processes, and it was managing the memory among those processes. But now we have a hypervisor is running multiple guest operating systems, and then are managing multiple guest operating systems, and then each guest operating system is running multiple user level processes, right? So now that's why the virtual address of a user process first converted into the physical address, and then into the physical address. Okay, so the hypervisor multiplexes the computer's DRAM between the operating system guest physical address spaces. Actually, the basic principle is same. Earlier, what we were doing, we were multiplexing the DRAM, or the physical memory, among multiple processes. And who was doing that? Operating system. Now we have multiple operating system, and hypervisor will multiplex the computer's DRAM or memory among multiple operating systems, right? So for that, just like operating system was using page table to translate or to multiplex the memory among multiple processes, hypervisor uses the extended page table to map guest physical addresses to physical addresses, or to multiplex the physical address among multiple guest operating systems. Okay. The EPT uses the same data structures as the page table, right? So the process of translating guest physical address to the physical address follows the same steps as we have seen in the previous lectures. The main difference is that the physical address of the data structure's root node is stored in the extended page table pointer EPTP field in the virtual machine control structures for the guest operating system. Remember, if you let me go try to uh, yeah, let me try to show you from the other slides. From this slide, for example, in in this case where we had single operating system, right? So for each process, there was a page table. And how we know where is that the page table is hierarchical, right? The top level is PML4. So how we know that where the PML4 is located in memory for a given process? By looking at the content of the CR3 register. Whenever a process is running, the address of its PML4 is laid, physical address of its PML4 is loaded in CR3 register by operating system, right? So operating system looks in CR3 and then finds the address of the PML4, and then it uses the fields from the virtual address, these fields, to consecutively index into these tables, right? If you remember from the previous lecture, to ultimately reach the lowest level, which is called page table. And when it indexes into the page table, it finds the physical page number, right? Now, exactly same thing is done or is to be performed for address translation between guest physical address to physical address. And where is the how we know the root address of the extended page table? Remember this translation here, this translation here, uh, this one, this mapping here uses, no, wait, sorry, not this one. This mapping here uses extended page table, right? So extended page table, there is a separate extended page table for each guest operating system, just like we had a separate page table for each user level process, right? Now for user level process, we were able to reach the location in memory where the page table is located by looking at the value of the CR3 register. Now how we can reach the extended page table for a guest operating system? When I say we, it's mean hypervisor. So for that, what does the hypervisor do? It looks at the EPTP field, extended page table pointer field, in the virtual machine control structure for the guest operating system, which basically mean that for every guest operating system, it maintains this structure, virtual machine control structure. Within this structure, there is a field which contains pointer to its extended page table, right? And then extended page table is used to translate guest physical addresses into physical addresses. Okay. Uh, it looks like there are some questions. Okay. How does the use of virtual addresses during address translation creates the illusion that each program has its own private memory? Anyone who want to answer, be quick. How does the use of virtual addresses during address translation create the illusion that each program has its own private memory?
Each program sees it as having access to contiguous memory via the use of the page tables, even though it's not actually accessing like continuous areas of data. The page table is able to sort it so that it looks as though that's what's happening from the application's end.
Yeah, that's correct. But a little better way of saying this is that this becomes possible because the address translation uh, allows or it presents the whole address range uh, to each process, which means it allows each process to generate an address within any within the whole address range, right? And how it does that? Basically by using the virtual memory, if you remember from the previous slides, right? I know what you are trying to say is correct. I don't know whether I was able to like improve the phrasing of the answer, but what you are saying is correct. Okay, next question. Is there any difference between the page tables and the extended page table as far as how they work? Anyone want to answer? like in terms of the working principle, is there any difference between page tables and the extended page tables? Please go ahead if you want to answer. No. So, I mean, the working principle is same. It is like just like I will explain in the next slide. This is like two level of address translation, but at the each level we apply the same principle. Okay. So, why does a virtual address have to be translated more than once in virtualization? Yeah, because see, we have only this physical memory, right? So what you need to do is that let's say you need to let's say I'm like breaking it into different blocks, right? And let's say now I have 4 blocks, and on this physical memory is, let's say, shared among 8 guest operating systems, right? So you cannot like serve the request requirement of 8 operating systems at the same time, right? Because you always have limited memory, right? So what you will do, remember the principle is same. Just like one process does not need to run whole of its code at once in the same time, an operating system does not need to execute the whole of its code at once, right? So what we can do is that we can load in the memory only that part of an operating system which is running, right? And then if it is not how to say, that part of that code of the operating system is not needed, or it is not actively used, we can swap it out and we can load the code of another operating system, guest operating system, let's say it is OS2, into the same block of the physical memory, right? So, but let's say, so this is like one level of multiplexing. So we are multiplexing this chunk X between OS1 and OS2, right? This is one level of multiplexing, right? Now, for the time window when this block X was assigned to OS1, multiple processes are running under this OS, right? Like process, let's say 1 to, I don't know, process 10, right? And we need to multiplex this chunk X for the time window when it was assigned to OS1. We need to multiplex this chunk X between processes P1 to P10, right? This is the second level of multiplexing. So first level of multiplexing, it is achieved by using extended page table, right? Multiplexing between operating systems, and multiplexing between multiple processes is achieved using page tables, okay? Uh, Okay, why does the VM store the location of the extended page table in the VMCS? Okay, first thing, when you are writing the question, write not directly to me, but to everyone so that even other students can see it, okay? So, the answer to your question is, I think it is a design decision. I don't know what will be the trade-offs behind that, but it can be, the information can be stored in some other structure. Why they used VMCS, I'm not sure about that. Okay, let's continue. So the OS maintains a separate page table for each process, and a hypervisor maintains a separate extended page table for each of the guest operating system. Okay. Now, anyone who knows how this figure was working, how actually what is this figure describing is like how you do the two-level address translation. First from the process, a virtual address space of the process to the guest physical address space, and then from guest physical address space into the physical address space, right? So if you have any questions about this, please write them quickly. And if no question, write no question. Okay. Now let me explain, and then at the end I will take care of your questions. Okay. So keep this figure in mind. At the top, you have the first a process generates an address, right? Here the first a process generates an address. That address is converted using the page table into the guest physical address, and then in the next step, that guest physical address is converted into the physical address using extended page table, right? So the translation starts from the virtual address and ends at the physical address. Okay, so how it works? So these dotted tables, they are guest level, they are the guest level PML4, right? How I can explain it to you? So first, let's focus that we are converting. In the previous lecture, we have seen this step, right? How we can use the page table to translate virtual address into the physical address, right? But now we are going to actually first look at translation from 2 to 3, right? So you have this uh, guest address, right? And then you break that address into 4 different components, right? Uh, so here you have this address, right? So this address is broken down into 4 different fields, just like in the previous lecture, we divided the virtual address into 4 different fields, including other than offset, right? So the guest virtual address is divided into PML4, into PDPT, but again, it is the PDPT in the guest table, right? In the EPT, page directory and page table. And at the end, you have the physical address, right? So if you have this physical address here, you have received the physical address, then you use the EPT to convert. So if you have the guest physical address, you use the EPT to convert it into the physical address, right? I will walk you through this, but this is just like high level figure, right? So once you have address here at this boundary, then you will use the EPT to convert it into the physical address. So you have guest physical address here, right? But how you get the guest physical address? By going through all these stages, right? Okay, now let me walk you through. Suppose you have this address, this one here, and this address is the virtual address generated by the process. Keep in mind the figure where at the top you have the virtual address, then using page table you convert into the guest virtual address, and then using extended page table you convert into the physical address. So this is the address generated at top by your process. So it is the virtual address, right? It is exactly same what we have seen. The template is exactly same what we have seen in the previous lecture. You have offset, you have page table entry. Actually, it is page table entry index, right? So it is page table address, this is PDEI index, and so on. This is PDPTE index, and this is PML4 index, right? Now, how it works? Remember, we said that in the virtual machine control structure, the hypervisor will maintain a virtual machine control structure, and in the virtual machine control structure of each guest operating system, there will be a field which is called EPTP, right? So if you have, like, let's say you have, I'm just naming it OS1, right? And this is OS2, right? So if hypervisor is, let's say, taking care of address translation for a process running within OS2, right? So let's say this is virtual machine control structure for OS2, right? So what will a hypervisor do? It will look into the EPTP field within this virtual machine control structure. And this is that field, right? So this field will now point to a table. Again, where will be that table? All of these saved tables are in the physical memory. So where is this table? It will point to a table, and this table is in the physical memory, right? Now, what are the entries within this table? So it points to the EPT. So in each entry of this table, you have a pointer to a PML4, and one PML4 is for one process. Like, let's say this is for uh, process X, right? And this is for process B. Actually, I have already written here. I don't need to rewrite it. I already have included it. I just need to highlight it. So this is for process A, this entry. Maybe this entry, red entry, is for pointing to the PML4 of process B, and this orange entry is pointing to the process PML4 of process C. Why? Remember, we have multiple processes running within each guest operating system. So this EPT is for the whole operating system Y, right? And this is the EPT for whole operating system X, and this is the EPT for whole operating system Z, right? But since the virtual machine control structure of the current operating system for which the hypervisor is taking care of the address translation is OS2, so that's why we are referring like its EPTP is referred, or it is accessed, right? Is everyone clear until this point? If not, please let me know. I mean, I haven't done anything like complex at this point, right? Okay, so EPTP points to this table, right? But where in this table, in which entry of this table we are going to access? EPTP gives us only starting point of this table, right? But it doesn't tell us like which entries need to be accessed, because each entry is for a separate process. Remember, for PA, PB, and PC. So for that, what we do is that the guest operating system looks in the CR3 value in the CR3 register. So that will tell us which entry is to be indexed or accessed, the content of the CR3. Let's say it points to this orange entry, which is basically process C, right? So it means that we are going to access the PML4 of process C, right? Okay, we have not yet used this address. Okay, we use the hypervisor uses EPTP to look into to access the extended page table, and then guest operating system running under the hypervisor uses the CR3 to access the PML4 of a process, right? Now we will use these addresses. So now using PML4 index, using this field, we use this field as an index and access this entry, right? What will be the content of this entry? It will give us an address to a page uh, page directory pointer table. Okay, and then we index into this table using next field, page directory pointer table entry page directory pointer table entry index. Okay, so we look into this entry, and what will be the content of this entry? It will be an address, physical address, pointing in memory where you have page directory. Okay, now using using the next field, this field here, you index into the page directory, right? So when you index into when you use this value or this field as an index, its content will basically give you again the physical address of the page table, right? So you access the page table, but which entry need to be accessed in the page table? You find the entry using this next field, page table entry index here. Okay, and content of this field is basically a physical address, right? Now here is the difference as compared to the previous lecture where we were converting only virtual address to the physical address. The output of this page table, the content of this page table entry, it is a physical address, but what happens is that as uh, it is used as the address to the guest PDPT. I know it is getting complex. So this address, physical address, which we access from the page table, it is treated as the uh, address of the uh, page directory pointer table, but guest PDPT, not the not the PDPT where we have only translation from virtual address to the physical address. And again, we repeat the same process. We break this address again into the fields. So here you have offset anyway. I didn't write it here, but here you have offset. I'm not writing it because it takes time. So this field is PML4I, PDPTE index, PDE index, PTE index, right? And then you use them to access the PML4. Okay. So this address, this whole address which you get uh, is pointing to uh, PML4 EPT. Okay. And again, you look into this and using the field, this field, you use it as an index. It will give you a content which will be actually the physical address of the PDPT. Sorry, which will be the address of your address of your page directory pointer table, and then you will repeat the process. So just to abstract the things here, so first you have, let me go back now here. First, you have PML4 address, right? Guest PML4 address. And you convert it into the PML4 physical address. Here, this one. PML4 physical address, right? Where is that figure? Yeah. And then this the value which you read out from the PML4 physical is treated as guest PDPT. Here. The value you read out, this one is treated at guest PDPT, and then on top of that, you again repeat the procedure, this whole procedure. I know it's kind of complex, but if you are clear on how to convert a virtual address into the physical address for non-virtualized environment, so if you are not clear, go watch the previous lecture and then go through these slides again or this recorded video again. Okay, up to this point, and then it will become clear. Let me check if there are no questions. Really? Okay. Okay. Now write down any questions you have related to execution context. If you have no questions, please write no question. But if you have, and then write the question. What is the purpose of feature specific registers? Okay. When you say guest for the PML4, those are the guest operating system on the hypervisor. Yes, that's correct. So during a time, all the register value gets saved and loaded, but what exactly counts as CPU local data versus thread local storage? Okay, I will answer it later. Okay, after covering the slide. Okay, so execution context. What is the execution context? Execution context of a thread is the values in registers needed or used for its execution, right? Remember, what is a thread? Thread is nothing but a sequence of instruction, right? So it is sequence of instructions. This is called a thread. And but to execute the sequence of instructions, you need a certain set of registers. If you remember from your machine organization course, what was this? Assembly programming machine organization. When a program executes, it uses the general purpose registers and maybe also special purpose registers, right? So those registers together, which are needed for the execution of a set of instruction or execution of thread, are known as the execution context. So execution context switch from thread A to thread B. How context switch happens? So first we store the execution context of A, thread A, that is the value of the registers used in A's execution from registers to memory. And then we load the execution context of thread B from memory to registers, right? So which basically mean, let's say this is a thread A, this is a sequence of instruction, and you have another sequence of instruction. Maybe both of them belong to the same program, right? So, and let's say you have a single core, right? And within the core you have registers, right? So if A is executing, all those registers here, I'm just indicating it with R, the register file. So when A is executing, there will be some value stored in the registers within the register file, right? So now if operating system decides that it is time to kick the thread A out and allow the thread B to run the core, so what should be done? The values in those registers, they cannot be lost, right? So what we do is that we put them in the memory. So first, all the value of the register files, not all, but those registers which are needed, right? They will be stored in memory, right? And this is known as like we are storing the context of the thread A, right? And then we uh, allow thread B to run, right? Let's say B, it is the first time for B to run, right? So now if B is running, it will modify these registers again, right? I'm simply indicating the modified values of the register file or registers in the register file as a RF bar, right? So when in future operating system decides to kick out the B, what will it do? So previously it stored the context of A in form of RF indicated as RF. Now it will also store in memory the context of the thread B, which I'm indicating as RF bar, right? Now if after B again operating system allows the thread A to run, what it will happen? It will move all the stored values back into the registers, right? So this is what we are saying here. You store the execution context of A, that is the value of the register used in A's execution from registers to memory, and then you load execution context of B from memory to registers, right? So this is how you can do the context switch from thread A to thread B. So what registers are used in the are like what registers make the execution context, right? So there are different registers and we need to store them depending upon which one of them are used and which one of them are not. So like you typically store the 64-bit registers which are currently used by a thread, by the execution of a thread, right? So these are general purpose registers. And then you also need to store the pointer instruction register, which actually points to the instruction count to be in next instruction to be executed. Let me just erase these drawings here. Okay. Other than that, stack pointer register, it also need to be stored in the memory when you are doing the context switch. What is the use of this register? It is actually used by procedural call instructions, for example, call, return, or push or pop. Now, if you remember again from your assembly programming and machine organization course, what we were doing there, whenever you were making a function call by using the call instruction, so you were supposed to save the registers on the some registers on the stack, right? And one register which was automatically stored on the stack or pushed on the stack by your hardware was instruction pointer register, right? And one register which was automatically popped from the stack when you do the return from the callee function at the end of the callee function, that was the instruction pointer again. So the value was like popped back from stack into the instruction pointer. Stack is what? Stack is a location in memory, right? Stack is a data structure which is maintained in the memory, right? Uh, Flag register, it actually holds different flags. For example, carry flag used in various instructions. For example, comparison. Again, you can uh, try to recall your discussion of status register in the context of your assembly language or machine organization course, right? Uh, Other than that, we have some additional registers, code segment register, data segment, extended data segment, and stack segment registers. So these registers, they were actually used in the Intel processors for managing the memory before the arrival of paging. So when the paging was not introduced, so then the memory was managed in the form of segments, not in the form of pages, right? And to manage those segments, these registers were used by the operating system. Okay, so these registers are still there, but in 64-bit Intel systems, they are unused. But in Intel 32-bit Intel system, they are still used because are at least if the paging is not there. Okay. What is the job of these two segment register, FS and GS? So the FS register, it points to thread local storage. Now, what is thread local storage? Anyone who want to answer? If you want to answer, please unmute yourself and go ahead.
Wouldn't it just be a cache for that given thread or like core?
No, no, no. Anyone else?
Is thread local storage the just the values of all of the registers?
No. Okay, let me explain. Actually, this concept was covered in operating system course, but I guess most of you have not taken that course, so that's why it's fine. Okay, so thread local storage is like, let's say you have a global variable A, right? And it is, when I say global, it is visible or it is shared between two threads, thread 1 and thread 2 of the same process, right? So uh, which means that if thread 1 up, let's say the value of A is 10, right? So if thread 1 updates the value of writes the value of A from 10 to 11, so then thread 2 will see that value 11, right? But what if there is a situation where we want both of them, T1 to T2, the same variable A, but we don't want to mess with each other. So basically, we don't want T2 to see the updates by T1, and we don't want T1 to see the updates by T2. So we are basically saying we want to have the variable with the same name A for T1 and another variable with the same name A for T2. So we want both of them to have the private copies, right? So for that, what we do is that we declare variable A as thread local storage. So we say, yes, we are declaring a global variable, but when we specify it to be a thread local storage, so what will happen is basically that two separate variables will be used, our private copies will be used, for one for thread 1 and one for thread 2. Okay, so both of them will be, and both of those private copies will be local to their respective threads. That's why they are named as thread local storage, right? But this is very simple example. Here we are saying only one variable. Maybe there is more than a variable. Maybe there is, you are making an array and you are saying, I want to use this an array as a thread local storage. So both threads have the private copy, right? So this register points to the memory location where your thread local storage is located, like for example variable A or that private array which I just referred in the example. Okay, so it is a mechanism which allows each thread to have a private copy of certain data, and the GS register, it points to CPU local data. So what is example of like CPU local data? For example, if you want to keep track of like how many interrupts are handled per CPU or pointer to current thread running on the core. So this is like per CPU information. Every core or every CPU, it will have its own value for these items, like how many interrupts it has handled at until a given time point. What is the which thread is currently running on that particular core, right? And all this information is stored in the memory location, which is pointed to by the register GS. Okay. Okay, now let me go to the questions. Again, let me check the time. So dealing with all the is very saved and loaded, but what exactly come? Okay, so during a context switch, all the registers values get saved and loaded, but what exactly count as CPU local data versus thread local storage? I guess I answered it, right, OVL? If not, write in the text that you didn't get answer for your question. So what is an execution context and why does the CPU need to save it? Okay, here is the question. What is the execution context? I gave the answer already. And the second part of the question is why does the CPU need to save it? Anyone who want to answer why does CPU need to save are actually the operating system, not CPU. Why the operating system need to save the execution context of a thread? Anyone who want to answer, unmute yourself and go ahead.
In order to context switch.
Yeah, in order to context switch in the future so that you can safely resume the execution of a thread which was previously kicked out from the CPU, right? So you can start from the same point where the execution was stopped for that thread. Okay, next question. Can you go over what the FS and GS registers are? Actually, I think I just explained. So FS points to the thread local storage, the part of the memory where the thread local storage is located, and your GS points to the memory location where you have CPU local data stored. Okay, does changing the execution context affect program security? Uh, Yeah, if it is not done properly, then it can affect the program security. For example, if during the context switch, let's say the program counter which points to the next instruction to be executed, if it is not saved, or if it is saved but then before it is restored in future, before it is restored, it is modified by some malicious program in the memory, then it can create problems, right? What parts of a thread execution context must be saved and restored on a context switch? We just mentioned them, right? All those registers which are needed for the faithful resumption of a thread in the future. How many threads can we have when we thread switch? I didn't get the idea of this question. We can have like you can have like if you have two cores, you can run two threads, you can run four threads, you can run eight threads, so on, right? But as you increase the number of threads and you keep the number of cores fixed, the competition between the threads increase because the number of cores are limited, right? So there is no such thing as like how many maximum number of threads we can have when we do the thread switching. Definitely your performance decreases, but I mean there is no how to say uh, conceptual limit on number of threads. Uh, are the segment registers repurposed in 64-bit register? Yeah, some of them. We will talk about them. Okay. So when we say we repurpose, so these CS, DS, ES, SS, they are not used in Intel 64, where we are using paging. Or even if they are used in a like limited way. But FS and GS, they are used in the same way as they were used before there was paging. Are repurposed to be used in the Intel 64-bit systems. Okay. Let me check the time. We have like 3 minutes. Okay. So execution, we are still talking about execution context, and we said that some of these registers will be needed to be stored in the memory depending upon which of one of them are needed for the faithful resumption of a or relaunch of a thread. Not only those registers, there are some other registers which are feature specific registers which also need to be saved depending upon which features are used by your program, right? So like if you have floating point unit, so all the registers which are the part of the floating point unit, they need to be saved. Similarly, SSE are streaming SIMD extensions. So actually all of these features, here is the point that all of these features, to realize them, there are certain set of registers which need to be used by a user process, right? So if a user process is, let's say, using instructions, SSE instructions, then the registers which are used by the SSE instructions, they need to be stored in memory when a context switch happens, right? Similarly, if a program is using floating point computation, so it will be using floating point unit. So if it is using floating point unit, all the registers which are related to the floating point unit, they need to be stored in the memory when a context, their values need to be stored in the when the context switch happens, and so on. Okay. So any feature which a process is using, the relevant registers need to be stored in the memory when a context switch happens, right? Now, how does the operating system knows that which of these feature specific registers need to be stored in the memory, right? For that, there is this XCR0 bit. This bit was actually, yeah. So this is a bit mask actually. So the bit 0, so for each feature, you have one bit specified. So in total, you have like 10 bits, right? So if bit 0 is set, it's mean that your program is using the FP use feature, right? Or it is planning to use, right? And if the bit at index 1 is set, it's mean that your program will also be using the instructions which achieve the SSE feature. Now let's say that bit at index 2 is 0. It's mean that your program or process will not be using the AVX feature related registers, right? So now by using this bitmap, you can specify, or the process can specify that which features will be used. And by looking at this bitmap, when the context switch happens, operating system will look at this bitmap. And let's say if it finds that the value of the at bit index 0 is 1, it will store the FPU feature related registers or feature specific registers in the memory, right? So how this bitmap is saved? So it is saved or how it is provided by using XSAVE instruction with requested feature bitmap, and how you restore using XRSTOR instruction. So all of these feature specific registers, they are stored using XSAVE in the memory, and then they are restored from the memory by the operating system using XRESTOR registers. Okay. And then to XSAVE instruction, RFBM is provided as an operand. Okay. Now, yeah, I think we should stop here. And okay, go ahead and do your class participation form. And I am here available until end of the lecture time. Okay. So I don't want to like interrupt you when you are doing participation form, but I have couple of things to talk about. Okay, let me give you the code, right? I think you will need code for your class participation form. So the code for today is, okay. Yeah.